So to start, let me give a recap of how global linear models work. And remember, there were three components to a global linear model: a feature vector f, this function gen, and a parameter vector v. So let me remind you what these are. So f is a function that maps any input-output pair to a feature vector. So let's take parsing as an example. So in that case, we might have x equals some sentence, that's going to be the input. Y is going to be some parse tree for that sentence. And remember, f is going to map an entire xy pair to a feature vector. So we might, for example, have this feature vector for this particular parse tree in conjunction with this particular sentence. Gen is a function that takes some input and maps it to some set of candidate structures. So again, x, for example, could be a sentence like the dog barks. Gen x is now going to be some set of parse trees, again assuming that we're looking at the parsing problem. And as we saw last time, there are various ways you might define gen of x. You might, for example, define gen of x to be the set of all possible parse trees under a context-free grammar. That is, under a particular context-free grammar. Finally, v is a parameter vector. So v is going to be some set of parameters of the same dimensionality as f. So if we have 5 features here, we would have 5 parameter values in v. So v, for example, could be this. And if we take the inner product between v and f, we get some score, which, as we said in the last lecture, can be interpreted as a measure of how plausible this particular structure y is when conjoined with this particular input x. So as we saw last time, the way we put these three components together is as follows. We have some set of possible inputs, for example, set of possible sentences in the language. This is the set x. I use y to refer to the set of possible outputs, for example, the set of all possible parse trees. Our goal is to learn a function, capital F, that takes an input x and maps it to some output y. So this function is defined through these three components, gen, f, and v, as follows. So for a given x, I enumerate every one of the candidate structures. So I do an argmax over all members y of gen x. For each such structure y, I calculate its score through this inner product, and then I return the highest scoring structure. That's what this argmax does. So it's very intuitive in a sense. You enumerate each of the candidates in turn, you calculate their score under this inner product, and return the highest scoring candidate. A critical question, of course, is given a set of training examples of input-output pairs, how do we actually set these parameters v? And we saw the perceptron algorithm for that. I'll give a recap of that algorithm in a second. But first, let's just look at this schematically again. This is a figure I showed in last week's lecture. You can view this whole process as follows. You have some input sentence. The function gen enumerates a set of possible structures. In this case, we have 1, 2, 3, 4, 5, 6 possible trees. Each of those structures is mapped through this feature vector mapping f to some feature vector. So I have 6 feature vectors, 1 for each of these trees in this case. And then we can calculate a score for each structure through the inner product between f and v. And so, for example, this first tree might get score 13.6, the second tree score 12.2, the third one 12.1, and so on. And then finally, we select the highest scoring tree, which is this first one in this case, because that has score 13.6, and that is the final output from the model. So again, you can see as these parameters v are varied, we will put different weights, either positive or negative, on the different features in the model, and these scores will change. And so in training the parameters of this model, intuitively we're going to try to look for values of v that correctly recover the correct parse on most of our training examples. So as we saw last time, a very simple yet effective algorithm for parameter estimation in global linear models is this variant of the perceptron algorithm. So let's look at this again. So the training set is a set of examples xi, yi for I equals 1 to n. So for example, I might have sentences paired with trees. We might have a few hundred or a few thousand or maybe even a few tens of thousands of examples like this. Initially we set all of our parameters equal to 0. And throughout this algorithm I'm going to define capital F of x in exactly the same way as before, this argmax function. So capital T specifies the number of iterations of the perceptron. It might be typically 5, 10, 20 or 30 maybe iterations. So that is going to specify how many passes we actually make over the training data. So we make big T passes over the training data. For each pass we cycle over the examples from 1 to n. We calculate the output of the model on the ith example. So z sub I is going to be some parse tree, which is the current highest scoring tree under the model. And if zi is equal to the truth, the yi, we leave the parameters unchanged. Remember, if it's not broken, don't try to fix it. So if we don't make a mistake, we leave the parameters unchanged. On the other hand, if zi is not equal to yi, we perform these very simple parameter updates. We say the new value for v is the old value of v, plus, and here I have the feature vector for xi together with yi, and then I subtract the feature vector for xi in conjunction with zi. Remember, all of these vectors are in d-dimensional space, and so while initially it might look odd to add parameter and feature vectors, it's a perfectly legitimate operation because these are vectors in the same dimensionality space. Intuitively, this is going to increase the weight for any features seen in the true structure yi and decrease the weight for any features seen in the incorrectly proposed structure zi. So that's the perceptron. As I said, it's a very simple algorithm, and yet it's a very effective algorithm. And in this lecture we're going to see how to extend this basic approach to the problem of tagging.